Okay, in this screencast on alcohols and ethers, we're going to look at reactions of alcohols to transform them into alkyl halides or sulfonate esters. And basically, that is a couple methods to take what is a bad leaving group and a hydroxyl group into better leaving groups as halides and alkane sulfonates to do further SN2 chemistry, which we learned last semester. We'll also look at a reaction called the Williamson ether synthesis that allows us to take alcohols and make ethers out of them. And then we'll look at a review of SN2 chemistry once we get an alkyl halide or a sulfonate ester in a molecule. How can we transform that into other functional groups using the SN2 reaction with different nucleophiles? Again, that's a review from 255. And then we'll consider some functional group compatibility issues when we're dealing with molecules that have different acidic functional groups, including an alcohol. How can we get around the acidic nature of the OH group to do some chemistry to sequence reactions together? So let's start and look at a couple reactions of alcohols. So first thing to note, the hydroxyl group hydroxyl group OH is a bad leaving group. So this holds pretty much for every reaction mechanism. We're going to learn with one caveat being the aldol reaction, which we'll learn later on this semester. In that case, it's allowed, but in general, it's not. So as we saw in the prior screencast, we typically need to activate the OH group first. So again, under acidic conditions, we're protonating it, and then we're forming that oxonium ion, which then can leave as the neutral molecule water. So that's what we mean by activate. So let's see an example of that. So if you're making note cards, maybe one technique you can do is, the functional group transformation, alcohol to alkyl halide. There I've just written it in words. And then, what is an example of an alcohol? So here's one. Let's just go ahead and review our naming so we know how to do that. So we find the longest chain. So just circle that in red here. Say that's the longest chain. That's 4 carbons, so this is going to be a butane derivative. And we see that the main functional group is the alcohol. And since it's not at the terminus position, we want to give it the lowest locant number. So we'll start our numbering here, 1, 2, 3, 4. So in terms of a progression, the longest chain is butane. The major functional group is the alcohol, so it's going to be a butanol derivative. So the E becomes OL. The alcohol is located at position 2, so 2-butanol. And then we see we have a substituent at position 3, so it's a methyl group. So then we could say 3-methyl-2-butanol. So that's the name of that compound. Say we're going to treat this with HBr. You can use HCl and HI as well, but not HF in general. So we're going to use this acid, HBr. Let me plug in the lone electron pairs on the bromine. This is delta minus, that's delta plus. Again, that's just from straight periodic trends of electronegativity. So what are we aiming to do? I said this was an acid, so this has to be a base. So we have an acid-base reaction happening. Let's just go ahead and draw this mechanism out. There's the acidic proton. It's going to be abstracted by the lone pair of the base. We're forming an OH bond, so we have to break that bond. Again, notice the flow of arrows starting at the lone pair, pointing to the electron deficient center, that's the acid. The double-headed arrow indicates the movements of 1, 2 electrons. This bond has to break. That's 2 electrons. They're pointing to the bromine, which is electronegative. It can accept those electrons. I'm just going to draw equilibrium arrows for this. So at this point, we end up with this ion pair. We have a cation and an anion. So now water has been hydroxyl group has been transformed into a better leaving group is water. It's going to leave. So this is an ionization event. So I'm just going to say minus H2O. Notice the conservation of the positive charge. We balance that out with the negative charge. And now this is a secondary carbocation. We recall carbocation stability. Tertiary is greater than, secondary is greater than primary. So once you determine what it is, you have to go to this trend, then evaluate. We're at secondary. Secondary isn't the most stable, tertiary is. Can this secondary carbocation rearrange to form a tertiary one? So you have to ask yourself that question. So how do we do that? The carbocation, we'll call it the alpha carbon. Any carbons attached to it are called beta carbons. That's a CH3 group. Then we have another beta carbon. I'm going to call it beta prime because it's not the same. So beta does not equal beta prime. And basically what you have to ask yourself is, can this thing do a rearrangement in the form of a 1,2 hydride or 1,2 methyl shift to become something more stable? So the beta carbon only has hydrogens on it. That will not rearrange because if it did, it would form a primary carbocation, and that's not allowed because it's less stable. So beta prime does have this hydrogen, which can migrate over. And when it does, it will form a tertiary carbocation, and this is a one-way street in terms of the mechanism. So we're no longer in equilibrium. So that hydrogen moved over. We have our bromide anion still floating around. Now that's the nucleophile. It's going to attack the electrophile, and what we end up with now is this secondary, tertiary alkyl bromide. And so if we were to name this, there's our numbering scheme. It's a butane derivative, so it would be 2-bromo dash 2-methyl butane. So in another different reaction, if we take that same alcohol, (3-methyl 2-butanol, and we treat it with this reagent, phosphorus tribromide, we end up with 3 equivalents of the following. So this molecule is 2-bromo, 3-methyl butane. So notice that under these conditions, the functional group transformation has taken place at the same location where the alcohol started. So we're starting at this 2 position of the hydroxy group, and then the hydroxyl group has been displaced by the bromine, so it's retained in that position. So obviously the mechanism of how this occurs with this reagent is different than what we just saw on the prior slide. So why don't we take a look and see how this is happening. So when you're asked to propose a mechanism of how something changes, I mean, you can see that you have to break this bond, CO bond. You have to break that, and you have to form a CBr bond. So there's no carbocation shifting or anything like that happening in this reaction. So how do we go about doing that? So let's go ahead and draw out phosphorus tribromide. And I'm going to put in all the lone pairs on the bromine atoms to illustrate a point here. So phosphorus is below nitrogen on the periodic table, meaning that in its normal valency it has 3 bonds and 1 lone pair. So what is unique about this molecule is that due to all these bromines, which are delta minus, we can basically put a delta plus charge on the phosphorus. Even though this has a lone pair, it's electron deficient due to so that this arrow on the bond here indicates induction. So these bromines are pulling electron density away from the phosphorus. It gives us this plus charge. And now in this case, the oxygen will act as the nucleophile to attack this phosphorus. And so that's what's going to happen. So even though the phosphorus has a lone pair of electrons, the oxygen is still going to attack it. And as we do that, we're then going to displace a bromine. So as we move forward here, we're going to end up with, at this point, oxygen is plus charged. We have the bromide anion floating around. We've balanced plus with minus, so we're charge neutral. Now this bond is activated to cleave because the oxygen is bearing a plus charge. So this will attack. This will cleave, and again, this bond breaks. The electrons go onto oxygen because it's electron deficient at this point, and it can accept them. So when that happens, we end up with our product. So this is basically, the SN2 mechanism you've learned from CHE255. So you can go ahead and review that if you're shaky on those details. So let's look at one more alcohol to halogen, and these are under a different set of conditions, but we'll keep the alcohol substrate the same. In this case, we're going to treat with this molecule here, which is called thionyl chloride, in the presence of this molecule, which is a base called pyridine. And what is going to happen in this is that a functional group transformation of alcohol to chlorine is now going to occur. So we've gone from a secondary alcohol to a secondary chloride. And this reagent, thionyl chloride, again, due to the presence of these electronegative chlorine atoms and the oxygen, the sulfur ends up being electron deficient. So oxygen will attack the sulfur. And now this next couple steps is very important in your understanding now and later in the semester about how the substitution happens at this point. The bond that breaks first is going to be this pi bond. So we have to draw this stepwise. So again, these mechanisms tend to get fairly lengthy. Just going to keep track of the electrons on the heteroatoms. So we form this. This will then collapse to do an elimination of one of the chlorines. And really overall what we're aiming to do is to activate that OH group so it's a better leaving group. And that's what we've done so far in the mechanism. We balance out that positive charge with the chloride negative charge. This then attacks. We end up displacing that leaving group with the Cl minus. And so you form this other byproduct. That's then going to basically decompose. So it will decompose to lose HCl plus SO2, and that's usually a gas that leaves. So maybe you can figure out the mechanism for that and convince yourself that that's what happens. Why is the pyridine in there? Because you are forming this HCl. And so what then happens is the pyridine acts as a base to form this molecule, which is a salt called pyridinium chloride. So these are a couple reactions to transform hydroxyl groups into halogens, and so just so we see it here, why? It's a question I get from a lot of students. Why do we need to know this? Why is this important? So again, briefly, OH hydroxyl group is a terrible leaving group. So that necessitates transformation into another functional group. So FG functional group. Transformation into another functional group. So we can do SN2, SN1, E2, E1 reaction mechanisms. So again, if you think of this as chess, a functional group transformation is like a move, and then the sequence of reactions altogether is like the strategy. Again, we're ultimately looking at sequencing these so that we can make something that's valuable to human civilization. So in this next slide here, we're going to look at the transformation of alcohols into sulfonate esters. Again, because sulfonate esters make good leaving groups, and then we can use those substrates in substitution or elimination reactions. So let's just look at a very simple alcohol, say ethanol, and again, we absolutely cannot do a direct substitution of OH for any other nucleophile. So we have to activate it, and that's what I'm going to show you the conditions to get another substrate that we can then use in other SN2 reactions. So I'm going to write the conditions down, and then I'll show you the mechanism of how this specific transformation happens. So this molecule is called methane sulfonyl chloride. And then we're going to run that in the presence of this base again, which is called pyridine. We're using a base because we're generating an acid that comes from this H and that Cl. So we form HCl that's neutralized by this base. So the product that we're forming is this, in this molecule would be called ethyl methane sulfonate. So organic chemists are fond of using abbreviations. So this would actually be abbreviated MS. This part of the molecule here, that's what this MS stands for. So OMS, that's a good leaving group. OH is not a good leaving group. But what is the mechanism by which this happens? So this sulfur, even though it's a heteroatom, is pretty electrophilic because you have these oxygens and the chlorine. They're pulling electron density away from the sulfur. So the oxygen of the alcohol is going to be a nucleophile which will attack the sulfur. The chlorine is not immediately displaced, so this occurs through a stepwise mechanism. And this is important when we get into the next module regarding nucleophilic acyl substitution. So here is what happens. Oxygen attacks this sulfur. We break a pi bond. We're now at this intermediate. We're going to go ahead and show this collapsing. So this is essentially elimination because we're reforming that pi bond. This leaves. So we have, at this point, an ion pair. So we've balanced out the plus with the minus. The chlorine is not sufficiently nucleophilic that it will automatically say come back and displace that as a leaving group by itself. So it's stable enough that this will sit there and allow the pyridine base at this point to come along and abstract that, so that we do end up with the methane sulfonate ester here, and then your byproduct that is coming out is the pyridinium salt. So again, anytime you have plus, minus, this is a salt, it's an ionic attraction. So that's why we're using the pyridine base in there. And so we can actually isolate this reagent here. There are other variants of these sulfonate esters that you'll need to be familiar with. So what I'll do is I'll write down, say, a table reagent. So I'm a fan of using tables anytime you can, so you can sort of see the trends. Trends are important. So another sulfonyl chloride. So this is para-toluene sulfonyl chloride. The abbreviation for that is TS. So we have the name, abbreviation, and finally, probably the best reagent to use is this. Which is an anhydride. So this is trifluoro methane sulfonic anhydride. And so this is installing, notice in this sulfonyl chloride, you have chlorine as the leaving group. In this molecule, this whole portion here leaves. So the oxygen of the alcohol will attack here. You break that, it eliminates, and then this whole thing leaves. So that's abbreviated TF. So these abbreviations are important to know so that you can actually, from this, here is what you should be thinking about. So the TS part is this whole group here. Again, the chlorine leaves in the mechanism. So why don't we look at, in the next slide, we'll put this into practice where we actually review this SN2 chemistry where we're activating an alcohol and then treating it with different nucleophiles. And again, this sort of all ties together in the sense that you learn spectroscopy in the first semester so that when you introduce another functional group into a molecule, you can then identify it using spectroscopic methods. So in continuing on with functional group transformations of alcohols, let's go ahead and use that reagent from the prior slide. So this ethanol derivative that has been activated with the mesylate functional group. And what we're going to do now is just draw a starburst pattern where we're treating this compound with various nucleophiles to proceed through an SN2 displacement of the electrophile with a nucleophile. So for example, if we have the compound sodium azide, so the azide anion will be the nucleophile, and say we were running this in acetone as the solvent. Again, remember the requirements for an SN2 reaction. We need a polar aprotic solvent. Acetone actually has this structure. It's propanone, a ketone, so it's polar aprotic. And basically, if we did a displacement of the O-mesylate as the leaving group, we would end up with this compound, which is an azide. So what you want to review as well are the functional group signatures. So I'm going to say functional group signatures in IR. So if we're carrying out this transformation and we wanted to verify that this N3 azide group was present, we could use IR. Region 2, if you remember from how I taught it in Organic 1, region 2 is the triple bond region. So there's an NN triple bond. You would see that nice sharp signature. Another reaction we could run on this material is if we were treating with potassium cyanide. So the cyanide would be the nucleophile in the reaction, and say we were going to run this reaction in DMF, as our solvent. And DMF has that structure, which stands for dimethyl formamide. We would end up with this compound, which would be propionitrile. And again, we would use IR to determine that the nitrile or cyano group is installed with the CN triple bond. So another example of a functional group transformation could be, say, the treatment with sodium ethane thiolate, and say maybe we wanted to run this reaction in, say, what solvent would we want to use? Maybe DMSO is another good solvent. So that stands for dimethyl sulfoxide. Again, these are good solvents for SN2. And so the ethane thiolate would be the nucleophile, so we would end up with, say, this compound, which is a sulfide or a thiol ether, which we'll learn about in Module 1 as well. So this compound, that might be a little tricky to use IR for, so maybe we'll use mass spec. Sulfur has a unique signature in mass spec, so you want to review that as well in the parent ion region. So one other common reaction for alcohols for the SN2 reaction is a named reaction called the Williamson ether synthesis, so that's pretty common. So say, for example, we were starting with that mesylate compound, and then we were treating that with sodium methoxide, and we're going to use methanol as the solvent. So we would end up with this compound, which is ethyl methyl ether. So the Williamson ether synthesis, you basically have some electrophile bearing a leaving group, then a nucleophile that has an oxygen nucleophile, and we're ending up with an ether. So we could use, say, if we were considering the unique number of carbons for this compound, there would be 3. So you have 1, 2, 3. You have a methyl group, and a methylene group. So it's good to remember what those things are as we refer to things. So that's CH3 is methyl, CH2 is methylene, CH is methine. So in terms of the unique number of proton signatures, those would be 3 as well. And again, we'll go a little bit further in what is the ratio, 3 to 3 to 2. And then just recall that the sum of that is 8, and that's the total number of hydrogens in that molecule. So again, as a word of advice in this class, I'll always try to keep what you've learned in your mind. So sort of ask yourself those questions as you go through and you're learning things, just so it's fresh. And so what I'd like to talk about now is sort of an application of all this to organic synthesis And specifically, let's consider a target molecule. This is our target molecule. We want to make that, and we are given the instructions to make that from this molecule using any other sources of carbon reagents that we need to transform this into this. So basically, when we're looking at this and this, we can see that we have 1, 2, 3 carbons, this hydroxyl group. So this is our map here. We see that there. We see 1, 2, 3 carbons. And then we see, okay, we have to make a bond between an sp3 and an sp hybridized carbon. So we need to make this bond. So it's clear we're going to displace this bromine with a source of sp hybridized carbon. So this would be a carbanion, so sodium acetylide. So if we were just considering a standard SN2 reaction, this displacing the bromine. However, the issue with this molecule is that with a carbanion can be both nucleophile, which is what we want it to do, or it can be a base. Remember, the action of a base is abstract protons. So in terms of rates of things, acid-base chemistry always occurs faster than nucleophilic chemistry. So I'm just going to write acid-base greater than nucleophilic displacement. So that poses an issue for us because we cannot just take this, treat it with that, and get that. We have this acidic proton that's gumming up the works, and it's going to basically deprotonate that, and then we're sort of stuck. So we actually need to transform this into something else that takes away the reactivity so that the action of this nucleophile on this carbon gives us the desired bond formation. So this gets to what's known as protecting groups. So for a lot of functional groups that we'll learn, there's a set of reagents called protecting reagents that can basically do just that. They'll protect them from certain reaction conditions, and then you can deprotect them. So for hydroxyl, functional group, we'll look at one of them, so called a silyl ether. And so what we would do is take that starting material, and then under these following conditions, we're going to use this silicon compound, which has 2 methyl groups, then a tert-butyl group, and then a chlorine leaving group. So if you recall your periodic table, silicon is directly under carbon. So it has a much larger van der Waals radii than carbon. So essentially what's going to happen is just a standard SN2 reaction in which this chlorine is displaced. So we're going to take this alcohol, treat it with this silicon reagent in the presence of this compound called imidazole, which is a base. And then we're going to use the solvent of DMF as we saw above. So So that's essentially, this base is going to neutralize the HCl that is formed in the reaction. And then we're going to bond oxygen to the silicon. So it's, you can think of it as SN2 chemistry with acid-base chemistry in there, and essentially what we are doing is we are removing that acidic proton. We're putting this protecting group on so that now we can treat this with the sodium acetylide. Say we'll run this reaction in DMSO. The sodium acetylide will attack here, displace the bromine. We end up with sodium bromide as the byproduct. I'm going to abbreviate this whole thing here as TBS. And that's going to form this product, TBSO. This is the new bond we just formed. Again, we're losing sodium bromide in that process. And so we've now been able to make the bond that we need to make, but however, we still have this group left on there. And so in a second step, we need to now deprotect that TBS group. So essentially, if you look, carbon, oxygen, silicon, we call this a silicon ether. And we can remove that by treating with this compound, tetrabutyl ammonium fluoride. And essentially what happens is the fluorine really likes to bond to silicon. So the fluorine will attack the silicon in an SN2 fashion, then this whole thing leaves, and then in the workup the oxygen gets protonated. So we will end up with this as our product. So this is currently run tetrabutyl ammonium fluoride and THF as the solvent, and that's going to then give us our product. So this has just been an example of when you run into what's known as this issue here. Is chemoselectivity, when a reagent can act upon different functional groups in the same reaction. Again, this carbanion, we want it to displace the bromine in SN2 fashion, but due to the kinetics, it's most likely going to deprotonate here first, which necessitates a protecting group of that OH as this silicon ether, which is abbreviated TBS. We can then treat with our desired reagent to do the SN2 chemistry. We end up with a precursor to our final product. It still has a protecting group on there which needs to be removed, and then we end up with our desired product.